and welcome back for this last sequence on reinforcement learning. Who has heard something about reinforcement learning? Well, a couple of raised hands, but everyone here has heard about reinforcement learning, because almost everything that comes out of DeepMind, including Alphago and the Go championship against Lee et al., all that is using reinforcement learning, which is really the hot area of research. So the previous 2 hours, I was sharing with you common architectures that you can reuse in your projects. I wanted to share with you the good practices in assembling the different Lego pieces and produce neural networks that were doing useful things. Now let's be a little bit more forward-looking and try to see how this reinforcement learning principle works. And for that, we will be using Pong, the game of Pong, yes, from the 70s. And what we will try to do is to train a neural network to play Pong from just the pixels of Pong. So initially, this neural network, it's not only that it doesn't know how to play Pong, he doesn't even know what he's doing here. He doesn't know that he's playing, he doesn't know what the rules are. And if this was a person, you would be teaching it by first explaining the rules and then having him play so that he gets the reflexes right, then maybe explaining some strategy to him. That's one approach, but we have around us examples of learning that happen in a completely different way. For instance, in the animal kingdom, a cat catching a mouse, well, the cat learns that somehow, but nobody explains to it what a mouse is and that you're supposed to catch it and that to catch it you're supposed to run and so on. So this is this reinforcement learning algorithm actually explores a different way of learning things. And Pong here is just an excuse, just an example to see how this can work. And again, we will be learning to play Pong from just looking at the pixels and, of course, having information about when a point was scored by us or against us. So we take the pixels, run them through a dense neural network, which I have represented here. And this is, we know the drill by now. We want at the end to produce 3 probabilities, so 3 neurons in the last layer, which will be activated by softmax. All of that is just as previously. And we want basically to classify this board position into a board position whether your next move should be to move the paddle up, should move the paddle down, or leave the paddle where it is. All right, so we will use the cross-entropy loss, and this time you will not be spared the formula. So this is the formula of this cross-entropy loss that I've been advertising since the beginning. And it is simply the multiplication of the correct answer multiplied by the logarithm of the predicted probability. Okay? So here, if my network predicts a series of 3 probabilities, P up, P still, P down, I take the logarithm and I multiply each by what I know is the correct answer. But how do I know that? How do I know this is the correct move at this point? If I know it, well, yes, I can do this multiplication, and that's my loss. And then I continue my algorithm, I have a loss, I can train my network, and so on. But I don't know what the correct move is supposed to be here. I have no idea. So we'll do it slightly differently here. Once we have those probabilities, we will sample from them. What does it mean, sampling from probabilities? Well, that means rolling a loaded dice that will produce a random output, but not completely random according to the probabilities that were computed. So if P up was super probable, it's P up that will come up most of the time. And if P down was very, very improbable but not completely, maybe P down will come up only once in 100. So that's called sampling from those probabilities. We take one possible answer, but we respect the probabilities of those answers. So let's say we sampled and we obtained up. So we move the paddle up by one notch and we keep playing. Just a little technicality that has to do with Pong specifically. In Pong, if you feed the board state, there is not enough information to see where the ball is going. If it is static. Here you can't see if the ball is moving forward, backward. So to give that information to the system, you actually feed the difference between two consecutive frames. On a difference between two consecutive frames, you see the trajectory of the ball. So that's just a wrinkle that is specific to Pong. All the rest is generic for all kinds of games where you have moves to play, and after you play a sequence of moves, at one point, a point is scored. And there, you know that there is at least something good in this sequence of moves if you managed to score a point. So this time, what you can do, once you have scored your point, for each move, you will compute this cross-entropy loss slightly differently. At each move, you know what your network predicted. You have those probabilities. So the red probabilities, P up, P down, P still, P down, sorry, they are known. You can compute those. And instead of the good answers, you put the move that you actually played. And the final difference is that you multiply all of that by the reward you got at the end. So if you won, the reward is +1, and you're adding this positively. If you lost, the reward is -1, and you are adding negative values to this loss. And now we have a loss. So now we can actually start training this system. We can compute this loss, of course, is computed from the probabilities. Those probabilities are computed by our neural network, which has weights. So we can derive this loss relatively to the weights. That obtains a gradient, and yada, yada, yada. We can know how to move the weights so as to penalize moves that ultimately made us lose and make more probable the moves that ultimately led to us scoring a point. Two little technicalities. The first one is that in this sequence of moves, of course, what you did at the end is probably where you did something correct. The fact that you bounced the ball 3 minutes earlier is probably less relevant. So it's not always the case, but it's customary in reinforcement learning to apply a decay factor to your reward across the time steps. And here I simply simplify this loss. It's exactly the same formula, but you realize that the sampled move is a vector that contains 1, 1, and 2 zeros, so this formula always simplifies. You always keep only one of those 3 terms in the sum, and it ends up being the reward at some step multiplied by, at that step, the computed probability of up, still, or down, whichever you chose at that step. And the second trick that you usually have to apply as well is to normalize all those losses because, well, I won't dwell too much onto this, but usually you have many of those steps that led to you losing, and only a few where initially by chance you hit the ball and score a point. And when you normalize them, well, that assigns kind of equal weights to those two instead of having a training data set that is heavily imbalanced towards you losing. All right, so this is how your training data set will look like. For each move, you know what your network predicted, you know what you actually did, and you know what the discounted reward for this move is. Because you played until the end, you computed the reward, and you discounted it across this whole point. And of course, you restart your discount every time you score a point, you restart this again. So the data set looks like this. It's just a big table of numbers. And on this data set, the loss is simply the multiplication of everything in one line. A couple of hyperparameters, because it's not, you don't train these things exactly as usual. Here, for instance, the batch size, we are using 20,000 moves at once. So we play many games until we accumulated 20,000 moves, along with their rewards and all, and their computed probabilities and all of that. And then we apply the backpropagation, the loss and backpropagation once on that batch. It uses RMS-prop as an optimizer. There is a whole collection of optimizers. We used this one and it worked. And the architecture really is as simple as a one hidden layer neural network. This was to test whether this really needed complex architectures or if it could work with something as naive as that. So how would you write this in TensorFlow? So again, we won't go through the entire code, and it's missing bits and pieces, but I just want you to spot where those big pieces are. Initially, we have a first here, a dense layer that will read the board. Observation here is, as I said, the difference between two frames of the board itself. A second dense layer after it that implements the softmax. So you see here you have two dense layers, and in the code you see them twice here. Then this produces a set of probabilities. I sample from those probabilities. In TensorFlow, you do this using this TF multinomial function. And if you are surprised not to see the softmax here, it's because it's done automatically inside multinomial. Then, and you obtain a sample operation. In the same way as when you ask an optimizer to minimize your loss, you obtain a training operation. We haven't touched so much on it yet, but we talked about it a little bit. I want to stress again that TensorFlow uses this deferred execution model. Everything you build in TensorFlow builds a graph. So when I do tf.multinomial, I don't sample at that step. At that step, I create a node in my graph that does the sampling. Okay, and it will be somewhere in the graph. When I will want to actually sample a move, I will have to do something extra, which I'll show you on the next slide. So up to now, and at the top here, I have placeholders which will receive values. So this is the placeholder that will receive the observations, that will receive the actions that were actually sampled, and the one that will receive the rewards when we finish our game and we have all of those rows with their rewards, with their discounted rewards. That's where we will be feeding them. And why do we need all those things? Well, we need the observation because that's what we run through our neural network to produce the probabilities of the next move. We need these actions because that's how we compute our cross entropy, the loss function, which usually is the difference between what the network predicted and what we knew to be true. In this case, is, as we said, the difference between what the network predicted and the move we actually made. Okay? And finally, the rewards, because the rewards is what allows us to compute our loss in the end. And you remember this formula, the reward goes here. And so now, how do we run it? So up to now, we have seen only high-level TensorFlow using the estimator API, where you do train and evaluate. And I wanted to show you low-level TensorFlow when you implement your training loop yourself. So in TensorFlow, as I said, everything is a graph. When you want to actually obtain a value by running this graph and computing something, you have to use a TensorFlow session. That's what I define here. And then you see I have two session.run operations, one here, one there. The first one runs the sample up, so that is what will actually run my neural network and actually sample from the resulting probabilities and actually give me a move to play. And the second one is at the end, is my training operation. So this we've seen before. This training operation is what actually modifies the weights and biases in the system to train. The rest is pretty standard. This here is one game. We initialize the game state. We read the pixels to compute the difference between two frames. Then we use our neural network to predict the next step, and we use the sampling operation to sample from the predicted probabilities and obtain the next step. And we call our Ponk simulator with that action so as to obtain both the next board state and also the rewards, the information about are we done, is the game finished or not, and so on. And we stack all of this information for later. Once a game is finished, it's finished in 21 points, we compute all the discounted rewards for all the points marked in the game, and that's our one batch in our training data set. The two last lines is that we run one training step in this data set. And you remember that in our model we have defined placeholders. Now I said if you want to actually run something, you use session.run, but it will not run unless you provide now actual values in the placeholders. And that in TensorFlow is done using this feed dictionary here, feed dict, this feed dict where I fill in my placeholders. Observations is my placeholder, and this is the value. Actions is my placeholder, and this is the value. So that's about it. Do you want to see it play? Let's see it play. Here we go. So, in brown, we have the computer, which is a highly programmed artificial intelligence, which uses the highly advanced algorithm of always leaving the pedal at the same height as the ball. It cannot be beaten. The only weakness is that its pedal speed is limited. So if you manage to hit the ball at a very, very steep angle, the ball might go faster than the pedal speed, and that's the only way you can score a point. On the green side, we have our neural network. Remember, initially, it's not trained. It doesn't know how to play. It doesn't even know what game it's playing. It doesn't even know what it's doing here. But we give it a whack on the head every time he loses, and we give it a piece of candy every time he wins a point. And using this reinforcement algorithm mechanism, well, it's not doing too badly. It's only 2 points behind. And look, those 7 points, he scored them the hard way. The only way you can win against this AI is to hit the ball on the very border of the paddle to send it flying at a very steep angle, and that's the only, like here. So using this completely brute force algorithm, I really don't find it clever at all. It's totally brute force. We actually managed, look, they are even. We actually managed to teach a neural network to play this game and beat an opponent that is really hard to beat if you do it manually. Some things you can notice is that, I don't know if you see it, from time to time it jitters a lot when the ball is far away, But when the ball is closer, sometimes it just stays put and waits for the ball to come. That means that it has learned to predict the trajectory of the ball. It has enough neurons in this mini neural network to predict the fact that the ball will bounce on the wall and come towards the pedal, and he can just stay where he is. And it won! 21 points. So this is reinforcement learning, and you can actually visualize what is going on, visualize the weights. Remember here, you have this neural network. So one neuron here has a weight for every pixel in this frame. And if you put those weights on a picture, you see how much attention it pays to each pixel in the image. And if you look at some of those, of course, we have 200 of them. So I just picked eight examples. Well, you see, some of them don't do anything useful. This is random noise. So this neuron probably doesn't do anything useful. And we are using a very, 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 very primitive neural network here. Really just 2 layers, dense layers. So we are not expecting this to learn well. This experiment was just to see if it will learn at all using this rather primitive, but I think also brilliant reinforcement learning algorithm. But you see other cases where you see the trace of the ball. So this neuron is actually paying a lot of attention to a ball that will come hurling this way. Or here you see a trace here, another one here. You see also that for some reason it's very sensitive to the movements of the opponent's paddle, which it shouldn't be. You don't get in Pong, you don't get much useful information out of that. But well, I guess it has trained to win. We are not saying that it has trained to optimum. So why is this significant? It's significant because it's the first mechanism that we have found for learning automatically, having a system that learns automatically just by playing. In a sense, it's not completely unsupervised learning because you are providing information about you won, you lost, but it's fairly unsupervised learning. And since it is fairly unsupervised, it has lots of applications. There are lots of ways you can use this to learn useful behaviors. And I have a couple of examples here, and maybe they will inspire you. So one is this Pancake flipping robot. Initially, they primed it by hand because priming a robot, here the network is sending currents to all the actuators of the robot. So sending random currents might be dangerous for a robot. That's why they prime it by doing it by hand. But then they let the robot play. Of course, the pancake itself is instrumented so that the robot has the information whether the pancake fell in the pan, if it flipped, or if it fell on the ground. And yeah, well, it's learning. It takes some time, but it's learning. And you will see that after 11 trials, it's still not very good. And it's really an end-to-end learning system. It has information from the pancake at one end, and it has this neural network that produces currents for the actuators, really currents for the actuators on the other end. And now it's flipping pancakes. Look, it's actually quite good at it. So in the same type of learning, we have this example from DeepMind. So DeepMind built a model where they used various skeleton structures and learned them to walk. So here the reward is simply if it falls down, ding on the head. If it continues, if you make progress in the X direction, you get a reward. And the model is predicting, within the constraints, the physical constraints of the skeletal model that they put in, the model is predicting how much power to inject in each muscle. And look what they got. Well, yeah, it does funky arm movements, but it has learned how to jump over obstacles. It has even learned how to crouch under very low obstacles. Look how it handles this. Yeah, they also did a quadruped model, which was actually very good at jumping. So this is amazing. It found how you can use your hind legs to push on the side of the plate and jump across the gap. This one is running through steps. And look, the jumps are pretty convincing. This is where it tries to do an obstacle race over rough terrain as well. And this is amazing, I think. Have you seen this jump? None of this was programmed. It had no information whatsoever apart from the physics of the skeleton and the fact that it will receive a ding on the head if it falls. And from just that information, using reinforcement learning, you have a complex behavior like this fantastic jump where it uses his arm to gain momentum, then stretches out, then cushions the fall at the other end of the jump. This one I find really impressive. Here it even learned how to jump across an obstacle. Now they are being goofy. They are pushing him around. And this is the training. It does lots of experiments. When it falls down, that's a minus reward. Here as well, it learns from the mistakes, and now he's up. Yeah, and this one is very good at jumping. And I like the way. And yes, this is really nice. Well, you can run like this. You can run like this as well. And it found it. It found out that you can run like this as well, and it works. Again, completely automatically. So, of course, you all heard also about Alphago, right? Alphago also, here I'm showing you move 78 in game 4. And normally when I say move 78 game 4, everyone goes, whoa, because that was the God move. That was the God move that Lee Sedol invented and allowed him to be the only human on Earth to have ever beaten Alphago. But other than that, Alphago was trained, well, it's a little bit more complicated than just reinforcement learning. But there is a lot of reinforcement learning in the process. And in a nutshell, what they did, well, in a game like Go, the algorithm for winning is actually pretty simple. You play all the moves until the end, and you find and then you continue on the path where you win most often. The only problem with that is that this is computationally too expensive to compute. So they build this neural network that can look at the board and say, well, this position is good for white or this position is good for black. And that neural network was built using reinforcement learning, and that neural network allows them to research the move trees to a much shallower depth, because instead of running, I don't know, 200 moves until the very end to see who wins, they can run only 3 or 4 moves and apply this neural network, which will tell them, oh, this is very bad for black, or this is super good for white, and they can stop there. And finally, I want to share this with you. We talked during almost 3 hours about neural network architectures. What is a neural network architecture? It's a layer like this with these parameters, another layer like that with parameters, layer, layer, layer. That's a sequence of characters. Haven't we seen neural networks that produce sequences of characters? Yes, recurrent neural networks, they produce sequences of characters. So what if we have a problem and we build a neural network that produces a sequence of characters that happens to be a neural network architecture that solves our problem? Well, initially it will probably not solve it very well, but we can train this neural network on our problem, let's say detecting airplanes, and at the end it will have some accuracy. We can take this accuracy and make that into a reward using our policy gradient reinforcement learning technique to influence the weights and biases in this neural network to produce a better architecture. And this is reinforcement learning used to generate neural network architectures that solve a given problem in an optimal way. This has actually been built at Google. It's called AutoML. And, well, it's still a tool. I mean, you still need a human to program the search space. This will be researching some types of architectures. So you still need someone to specify that. But in the end, you have a system that can devise neural network architectures. And here I'm giving you two examples. So this is a graph of a standard LSTM cell. So this is built by humans. This is the recurrent neural network cell that we have seen previously that is used, not the one that is used most often, but another one. And when the neural network was given this problem to produce a recurrent cell that would solve some problem very efficiently, it found this architecture, which has common elements with this one. You see there are additions here and so on, but otherwise is very, very different from something that a human would have invented. And it does solve the problem in a more optimal way. So I think this is quite intriguing as well, to see that by combining these techniques, combining recurrent neural networks that we've seen, combining the reinforcement learning techniques that we have seen as well, you can build a circular system that will generate neural architectures for you. This is very advanced. This is not something that I recommend you for your next project. But I kind of like where this is going. And with that, I thank you very much. And we have a couple of minutes open for questions. And after that, I will still be here to answer your questions. Thank you. Any questions? Questions? Yes.
Just a remark about the Pancake sample. I think that it makes sense for the neural network to learn to watch at the other pattern because how the other pattern behaves. Because it always follows the ball. So it makes sense that the neural network.
Okay. Maybe. So the question was that I said that watching the opponent's paddle is probably not so important, and you think that it might give him good hints. Yeah, you're probably right. You're probably right. Maybe as a human, that's something you don't see immediately, but as a computer, it might give you good hints, indeed. Other questions? Yes? So for the training example, the question was, how do you learn it? Yes, you need pairs of sentences. There are actually today quite big academic corpuses that contain pairs of sentences that have been handcrafted specifically so that researchers could conduct research on translation algorithms. So they are quite sizable data sets that exist for a lot of languages. And yes, you need a sentence and a sentence. The algorithm does the alignment inside of the sentence, so the attention mechanism finds out automatically which word corresponds to which word and handles difficult cases like one word translated into two in a different language or inversions and so on. But at least for the research here, you translate sentence to sentence. Yes?
For your plane detection example, you use 2 neurons for a binary classification. So why would you use 2 neurons?
Yes, that's a very good question. For binary classification, so in the plane example, why would I use 2 neurons? Yes, you can use only 1 neuron, and actually in the final version of the plane detector, when I have boxes, you have seen that I produce a single confidence number, C, which tells me plane or no plane. And that's a pain, frankly. Because, why? I won't explain it mathematically. Mathematically, it can be explained. But practically, it's a pain because when you have one number, then you need a threshold. And you need to say, so what is a plane? A plane is above this threshold or under this threshold. And that's another parameter to tune, and you never know where to put it. When you train 2 outputs with softmax, one of them is always higher than the other. And that's your threshold. But you don't need to set a threshold. And mathematically, it solves the problem of classification in a more pure way. So that's why for a classifier, even a 2-way classifier, yes, you have 2 classes, that's 2 neurons, softmax cross entropy. But very good question, yes. Maybe a last question? No, you're hungry, you want to go to lunch. I will see you at lunch, thank you.